Vibration analysis. Procedures for accurate evaluation of machinery condition. Part 1. In this Procedures for Accurate Evaluation Part 1, we will talk about the introduction, theory, calibration, frequencies generated, data collection, transducer selection, and continuous monitoring. Vibration analysis. Procedures for accurate evaluation of machinery condition. Introduction. Accurate evaluation of machinery condition is more difficult because Number 1, the same frequency spectra can be produced from various time domain signals. This is because the time signal contains phase and the various forms of signal distortion. Number 2, some frequencies are acceptable below certain levels, and other frequencies are not acceptable at all within prescribed calibration levels. Number 3, some frequencies can be caused by more than one problem. For example, the fundamental or 1 times revolution per minute or RPM can be caused by looseness, imbalance, bent shaft, misalignment, resonance, loading, pump starvation, open iron or broken rotor bars, and soft foot or casing distortion. The fundamental can also be measured in a machine coupled to another machine that has one of the above problems. Number 4, accurate analysis of one frequency often depends upon the presence of one or more other frequencies. The importance of the frequency domain spectra in various frequency ranges and the ability to zoom in on various frequency windows are stressed. The requirements for the time domain signal in various time ranges and the understanding of the phase between various signals are also emphasized. Some valuable data is lost when converting from the time domain to the frequency domain. This is why the same or similar frequency spectra are presented for very different problems, and why the time domain signal is required for accurate diagnostics. In fact, several time periods in various time ranges are required. This is true because all events may not be occurring in a given time period. High frequencies are not visible if the time period is too long, and low frequencies are not visible if the time period is too short. Problems that can occur in all machines, such as imbalance, bent shaft, misalignment, looseness, etc., are discussed separately. Problems unique to certain machine groups, such as motors, pumps, fans, turbines, compressors, etc., are discussed with that group. The importance of calibration and adjusting sensitivity for speed is also discussed. Vibration analysis. Procedures for accurate evaluation of machinery condition. Theory. The measured frequency tells what is wrong with a machine, and amplitude identifies the relative severity. Frequencies do not lie, although they can be misunderstood, measured improperly, or interpreted incorrectly. Amplitude, on the other hand, can be over or understated. Amplitude is not understood by most people and is often misinterpreted. For these reasons, amplitude, all by itself, is of little value and should not be relied upon. For example, a small fan could vibrate at levels up to 1 inch per second for years and not fail. On the other hand, a bearing with a cracked inner race could fail within days with an amplitude of 0.02 inch per second. Most of the vibration severity charts were designed for imbalance only. However, over the years these charts have been used and applied to all machinery problems. The net result is that machines fail, and the vibration level does not go up, in fact it often goes down. Consequently, people think it is a catastrophic failure. If diagnostics had been performed along with or instead of condition monitoring, some warning would have been obtained. Figure 1 is the balance tolerance nomograph, which contains a good balancing specification for rigid rotors during shop balancing. When using this graph, place one end of a straightedge on the rotor weight scale and place the other end on the rotor operational speed scale. Then read the allowable gram-inches of residual imbalance from the intersection of the straightedge and the center scale. This graph is based on IS 0-1940 and ANSI IS 2.19-1975 with some refinements. Figure 2 contains the operating machinery imbalance guide. This chart is a good guide for general severity of imbalance only. We do not know the origin of this chart. However, it may be a derivative of the Rathbone chart. Various versions have been published in several places. In some circles it is referred to as the IRD chart. Regardless of who deserves the credit, it is a good chart for imbalance severity and should not be used for other problems. Some frequencies are permitted at acceptable levels in some machines. Some examples are imbalance or one-time RPM, gear mesh frequency, vane pass frequency, etc. These frequencies should not contain harmonics, except for one-time RPM and fluid film bearings, modulation, or truncation. In other words, a good machine could have the above discrete frequencies at amplitudes of less than 0.2 inch per second. Other frequencies are not permitted at any level within the prescribed calibration levels. Some examples of these frequencies are oil whirl, all bearing frequencies, pulses, except in cutters, etc., noise, and fractional discrete frequencies. Most real-time analyzers have enough sensitivity to measure the balls or rollers passing under the transducer. If the calibration standards are not observed, or if auto-ranging is used, bearing frequencies could be observed without the presence of a significant defect. Previously, we have ever discussed how frequencies add, subtract, modulate, and truncate based on physics in an electronic environment. Sometimes rotating machines can behave in a very similar manner. A good example is a beat. If a 1776 RPM motor was belt driving a 1500 RPM fan, and the motor and fan were isolated from each other, the motor would be vibrating at a frequency of 29.6 Hz, and the fan would be vibrating at a frequency of 25 Hz. This is true when there is no mechanism to allow the two frequencies to beat. If the motor was mounted on the fan pedestal, then the two frequencies could beat. The flexibility of the fan pedestal is the mechanism that permits the two frequencies to beat. If the fan and motor mounting were isolated and the motor was loose, the beat would be felt on the motor and not on the fan. If the fan was loose, the beat would be felt on the fan and not on the motor. In both cases, the looseness is the mechanism that permits the beat. In these examples, the nonlinearity or looseness and flexibility in this case permitted the frequencies to beat. In other cases, two frequencies can be present, generated by the same machine, and they will not beat. An example would be imbalance and vane pass frequency. In such cases, a spectral line is present at rotating speed, and another spectral line is present at vane pass frequency. In this case, we have two frequencies in two problems or imbalance and a vane pass frequency problem. The time signal is that of a high frequency riding a low frequency. On the other hand, if the impeller was loose on the shaft, the spectral line at vane pass frequency could be modulated by unit speed. Modulations of speed could appear below and above vane pass frequency. However, more energy may be contained in the sidebands below vane pass frequency. Sidebands below the discrete frequency are in out-of-phase condition or looseness, and sidebands above are in in-phase condition or eccentricity. In some looseness problems, sidebands can occur on the high side when eccentricity is not present. This occurs because looseness goes in and out of phase. Remember, if frequencies are out of phase, they subtract; if they are in phase, they add. In either case, amplitude modulation occurs. In other cases, the various frequencies are not generated and then added together. In these cases, only the resultant time signal is produced. Remember, a perfect sinusoid contains only a discrete frequency. The only way to distort the sinusoid is to add some harmonic content. The distorted signal can take many forms, depending upon the harmonic content and the phase relationship of the harmonics. This signal is normally the discrete or fundamental frequency along with various harmonics and their phase relationships. Since phase is not presented or is discarded after the fast Fourier transform or FFT is performed, the time signal must be used to obtain phase for accurate diagnosis. If your analysis does not include the time signal, your diagnosis could contain up to a 20% error rate. Vibration analysis. Procedures for accurate evaluation of machinery condition. Calibration. Some frequencies at acceptable amplitudes are found in good machines. Some examples are imbalance, vane pass frequency, gear mesh frequency, etc. Other frequencies are not acceptable at any level within prescribed calibration standards. Some examples are the various frequencies generated by anti-friction bearings, pulses, bars, or corrugations on rolls, etc. In addition, spectra taken from good machines should not be modulated by shaft speed or any multiple of shaft speed. However, the data from most machines contain some sidebands. The reason for this paradox is that it may not be economical to fix or repair all identified problems. Most of the problems in determining what is good or bad can be eliminated by strict adherence to calibration standards and adjusting sensitivity to speed. This writer has used the speed-adjusted calibration standards for 20 years with outstanding success. See Table 1 in the next slide. Table 1. Speed-adjusted calibration standards. We can see the similar zero to peak between rotating machine and paper machine speed. For example, as we can see in the first row, the 0 to peak 0 to 0.70 will reach within 1000 rpm and above by rotation machine and 2400 rpm and above by paper machine. And so on. Another valuable utility of Table 1 is that problems of the same severity appear at about the same percentage of full scale for all speeds. For example, an imbalance problem on a 1200 rpm fan at 0.35 inches per second, or half scale of 0 to 0.7 inch per second, is just as bad as 0.05 inch per second, or half scale on a 150 rpm fan. Of course, the latter fan would not require balancing. However, if a similar situation occurred with looseness or bearing defects, a fix would be required. Therefore, automatic ranging should be used only in rare cases. Vibration analysis. Procedures for accurate evaluation of machinery condition. Frequencies generated. The fundamental frequency or 1 times RPM can be caused by imbalance. When a rotor has one heavy place, the weight of the heavy place, distance from the shaft center line to the center of the heavy place, and angular rate of velocity or speed all combine to create a forcing function or vector at some magnitude and direction. If the rotor has more than one heavy place, the weight will be the vector sum of all the heavy places. As the heavy place rotates with the rotor, a frequency at the speed of the rotor is generated. Several conclusions should be made from this simple example. Number 1, the industry standard for measuring machine speed is revolution per minute or RPM or feet per minute or FPM. Number 2, the industry standard for measuring frequency is cycles per second, CPS, now called Hertz, to honor the man who developed the frequency theory. Number 3, frequency identifies the problem. If the discrete frequency is not present, it will always manifest itself as a sum or a difference frequency. Number 4, amplitude identifies relative problem severity. Amplitude can be overstated by looseness and resonance. Amplitude can be understated by mass, rigidity, and damping. Amplitude can also be overstated or understated by the way most instruments measure amplitude. Harmonic content and signal distortion are other good ways to determine problem severity. All generated frequencies are equal to events times speed. For example, half-shaft speed is generated when an event is occurring every other revolution, as in some looseness problems. If a rotor has imbalance, the heavy spot rotates at the same speed as the rotor. When two events are occurring each revolution, as with looseness, bent shaft, or two high places on a roll, the fundamental and second harmonic are generated. If three events are occurring each revolution, as with misalignment, the fundamental, second, and third harmonic are generated. It also follows that Vp equals S multiply in V, where Vp is vane pass frequency, S is speed, and Nv is number of vanes in the impeller. For blade pass frequency, Bp equals S multiply Nb, where Bp is blade pass frequency, Nb is number of blade. And for the gear mesh frequency, Gm equals S multiply Nt, where Gm is gear mesh, and Nt is number of teeth. Some frequencies vary. For example, frequency is equal to the number of events times speed. If a rotor becomes loose or improperly adjusted, it could hit or strike the housing or some other object. The frequency generated can vary, depending on how many times it hits each revolution. The frequency will be the number of hits times speed. Note that vane pass, blade pass, and gear mesh frequency are all a specific harmonic of rotor speed. In some cases, it may be difficult to distinguish between a harmonic and another generated frequency, such as vane pass frequency, ball pass frequency, etc. In other cases, frequencies such as ball pass frequency inner race or BPFI or ball pass frequency outer race or BPFO may be close to a harmonic of rotating speed, or vane pass or ball pass frequency. In such cases, a frequency translator or zoom feature and the time domain signal are required for differentiation between the various frequencies. Accurate analysis also requires determining the phase relationships between the fundamental and the harmonics. Vibration analysis. Procedures for accurate evaluation of machinery condition. Data collection. Data should be collected in the load zone with due respect to flexibility. For example, imbalance is normally a radial loaded problem. However, imbalance in some cantilevered fans can cause an axial load. Looseness can be either radial or axial loaded, depending on where the machine is loose and how the machine is installed. Horizontal and vertical offset misalignment cause a radial load. Angular offset misalignment causes an axial load. Monitoring of small simple machines can often be accomplished by collecting data in the horizontal and axial directions on the drive and driven units across the coupling. Depending on time, workload, etc., one monitoring point at 45 degrees between horizontal and axial may suffice for monitoring. However, data must be taken in the horizontal, vertical, and axial directions when troubleshooting and establishing baseline data for new installations, and when new equipment is added to the program. Most failures occur on the drive and driven end of machines. Therefore, data must be taken on both sides of the coupling. Data should also be taken on the off end of the drive and driven unit in some cases. For example, data should be taken on the off end when the rotor is between two bearings. The location of where the data is taken also depends on what you want to measure. If a motor has the same bearing on both ends and one bearing is defective, often the location of the defective bearing can be identified by taking data from both ends. If the problem is a radial loaded problem, then data must be taken in the radial direction. Imbalance is a good example. If the problem is an axial loaded problem, then data must be taken in the axial direction. Anti-friction bearings and angular misalignment are good examples of axial loaded problems. When troubleshooting, data should be taken in the horizontal, vertical, and axial directions on the drive and off end of each machine in the complete machine train. For routine monitoring, it may be adequate to take data in the horizontal direction on the drive and driven end of each machine. For large motors, fans, and other equipment, it may be desirable to monitor both ends. Notes: these data collection procedures apply to equipment that doesn't have permanently installed monitors. Different rules apply to high-speed turbo machinery. The appropriate specifications should be reviewed in such cases. Vibration analysis. Procedures for accurate evaluation of machinery condition. Transducer selection. Transducer selection depends upon the job. For example, defects in anti-friction bearings for some speeds are best measured with a velocity transducer or an accelerometer. Lower speeds require a displacement transducer. If you want to measure how much one object is moving relative to another, or commonly called relative motion measurement, a displacement transducer must be used. Some examples are relative shaft motion in fluid film bearings and press or nip rolls, clearance in anti-friction bearings, amount of misalignment, and bend in a shaft. Much has been written on the selection and use of transducers, and most of it is inaccurate. The following rules may be helpful. Number 1, if you want to measure the amplitude of frequencies below 10 Hz or measure relative motion, a displacement transducer must be used. Some displacement transducers can be used to measure frequencies up to 1000 Hz. Number 2, for measuring frequencies between 10 Hz and 2000 Hz, a velocity transducer is the best selection in most cases. Number 3, for measuring all frequencies above 2000 Hz, an accelerometer must be used. When an accelerometer is used, it must be either screwed down or glued down. If this rule is not followed, the amplitude of some frequencies can be over or understated as much as 4 times. Also, some higher frequencies can appear as wide-banded noise and not as discrete frequencies with sidebands. Both situations cause serious errors in analysis. Accelerometers can be used to measure frequencies below 2000 Hz. However, the requirement for hard mounting is time-consuming and would not be the choice of an informed analyst. Number 4, when diagnosing problems in compressors and pumps, data from a pressure transducer is often required. These transducers are calibrated in MV per PSI and measure the pressure fluctuations in gases and liquids. Refer to the frequency response curves in Figure 3 in this video for transducer selection. Data is often required from more than one type of transducer for accurate diagnosis. For details description of this frequency response curves, it also could be found in the earliest video on the part of vibration analysis introduction on this channel. Vibration analysis. Procedures for accurate evaluation of machinery condition. Continuous monitoring. Without question, high-speed turbo machinery and other high-speed machines should be monitored on a continuous basis. The displacement transducer is the best choice for measuring relative motion of the shaft. One of the biggest problems is the failure to monitor transducer gap voltage. In some cases, a machine can fail, and the vibration level may not increase significantly. However, the gap voltage will increase substantially. The other problem is a misunderstanding of the frequency response curves discussed in video chapter Vibration Analysis Introduction, earliest video. The result is that accelerometers are not installed to monitor high frequencies. It is essential to monitor high frequencies with an accelerometer. If this is not done, the machine can wreck, and a warning will never be observed by the displacement transducer. The major cause of such failures is normally high-frequency rubs. Diagnostic technology has developed to the point that the computer is programmed to diagnose problems. This online or offline expert system is now available and is economical for most plants. Thank you.